In the previous video, we talked about the mechanism behind aldol condensations, how you first do an aldol addition, and then if you heat it up, the OH, the beta hydroxy group, will act as a leaving group. One of the alpha hydrogens will be ripped off by the base, and you'll basically do an elimination reaction. So you get an alpha-beta unsaturated aldehyde or ketone. In this video, we're going to assume that we have that whole scenario. We have heat, we have water, we have sodium hydroxide. We know we're going to get an aldol condensation product. We just have to predict what it will look like. Okay, so let's try it. Now first I'm going to draw this just to illustrate the point, and then I'll sort of show you how to draw it in from scratch on your paper. The idea is that two of these molecules are going to come together. So you can sort of trace over this to create another molecule. Two of these molecules are going to come together, but the oxygen is going to be part of the leaving group and the second one. So you can take the whole rest of the molecule and move it and put where the oxygen was on the alpha carbon. And that's your product. Notice that this is almost even a little easier than drawing the aldol addition products, because in this case, you keep the double bond there. You don't have to erase it. You don't have to draw any OHs in. And so that would be your product. Now, there is one other thing I would note about this, and that is that these double bonds can't rotate, and so the bulky groups tend to be on opposite sides. So truly, this other carbon chain would probably point in this opposite direction. So if you have your original molecule, and you're trying to draw the second one in, because on your piece of paper you can't just trace over it and then copy it and drag it along. So redraw this in and number the carbons. So you have 1, 2, 3, 4, 5. Awesome. We're going to add, this is going to be carbon number 1, and we're going to have 5. Now I'm going to go so that the big group is trans, or on the opposite side as the other big group. So 1, 2, 3, 4, 5. And that would actually be, the major product for this reaction. So if you're drawing it on your own, I encourage you to number the carbons. If you add carbons or remove carbons, it is a big deal, because that's always a big deal. The reactions that do that are very special, and so if you don't draw the correct number of carbons, the implication is that you think that this reaction adds or gets rid of carbons, and it doesn't. So that's how you can predict the product of an aldol condensation. You'll notice that this is an alpha-beta unsaturated aldehyde. You have alpha carbon, beta carbon, you have a pi bond or a degree of unsaturation between there. So it's an alpha-beta unsaturated aldehyde. Okay, let's try that same process with B. You could go through the same procedure. I think it's nice to see this because it emphasizes that it's the same molecule that's being attacked and attached to the original molecule. It's just the oxygen is acting as a leaving group. And so that carbon chain is attaching to the alpha carbon. Now, that's an awkward way of drawing it. And you could see that this is not the correct way quite yet. It's very much closer, but it's not the correct way. Look at how crowded this area is. There's a lot of steric hindrance there. All those groups are going to be repelling each other, bumping into each other, pushing each other apart. And that puts a strain on this molecule and prevents it from forming most of the time. Most of the time, you will have the trans product, or if you prefer, the E product. So to draw that, draw your original molecule, copy that down. And then on the alpha carbon, you want to have the double bond. And from here, we're going to copy the molecule, but we're going to make sure the bulky area goes in the opposite direction. So if we're numbering this original molecule, we can number this. We have our carbon number 1. I need 5, so 1, 2, 3, 4, 5. On carbon number 4, we have 2 methyl groups. And that is your final product. So you've copied the same molecule down. The only difference is the oxygen isn't there. That is left as a leaving group, and what attacked it, what replaced it, was the carbonyl, or was the alpha carbon. So you erase the numbers, and that is your beautiful product, the E, or trans product. Technically, it's the E product. The difference between E and trans is, in the case of trans, the groups that are on opposite sides of the double bond have to be exactly the same, whereas in the E product, they don't. Okay, so let's try this one. Now, again, just to prove the point that multiple versions of this same molecule are coming together, I'm going to trace over this molecule. But where the oxygen was, that'll be a leaving group, and I'm going to replace that with the alpha carbon. So that's a rough draft for this molecule. The one thing that's not right here, you can see you have the bulky groups facing in the same direction. So there's a lot of steric hindrance there. They would repel each other. They would repel each other, and that would be unstable, so it wouldn't form most of the time. So most of the time you would get the E product. This is the Z product. So to draw the correct product, we're going to copy down our original molecule. So we have our aldehyde. On the alpha carbon, we draw the pi bond, and now we number. So 1, 2, 3. Here's 1. We're going to have the carbon chain going in the other direction, away from the bulky group, so 2, 3. And that third carbon is going to be in a 5-membered ring. And so you can see that those are the same type of molecule. That this molecule here is really the same as this molecule here. The only difference, and maybe it helps if I draw the hydrogen in, the only difference is that where this double bond goes to an oxygen, this one goes to the alpha carbon. Okay, let's try it with this molecule. And again, to prove our point that it's just multiple versions of this same molecule that come together in a beaker when you have sodium hydroxide, water, and heat. I'm going to trace over this, and a second molecule attaches, it just attaches to the alpha carbon. Now in this case, both of the branches are the same size, and so that truly is your final product. If you were drawing this and you wanted to just make sure, just always make sure that you can number the carbon chain. So that's 1, so you'd have 2, 3, 4, 2, 3, 4 on one side, and when you're done with that side, you'd have 2, 3, 4, so 2, 3, 4, and so you see it matches. So I encourage you to number it just to make sure that you have the right number of carbons. Because these branches are the same, it doesn't matter if you switch them. So this is your final product. Let's try it with E. All right, to prove or just to make the point that it's a second version of the same molecule, I'm going to trace over this molecule. Just where the oxygen is, that's going to be our leaving group, so we won't have that anymore. Instead, that double bond will connect to the alpha carbon. Now, that is the only product that you have here. That's the only way you can arrange those atoms, so that would be your final product. If you were drawing this on your own, because I know it's different just tracing it as opposed to freehand drawing it. So if you're freehand drawing it, draw the original molecule once, and then on your alpha carbon, draw the pi bond and number. So we have a 5-membered ring, so we can put a 5-membered ring here. And then on the other side of the 5-membered ring, you have a benzene ring, so we can add in a benzene ring. And you'll notice either way you get the same product. Okay, let's try it with F. So this first molecule is going to react with another version of this same molecule, which is why I'm just going to trace this. In the second molecule, the oxygen will act as a leaving group, so it won't be there anymore, and it will be replaced by the nucleophilic alpha carbon. And so that alpha carbon will be there. And notice in all these examples, we have alpha-beta unsaturated aldehydes or ketones. So here's the alpha carbon, the beta carbon. There's a degree of unsaturation, the pi bond there, and so these are called alpha-beta unsaturated ketones or aldehydes. And that's your final product. So you just redraw the molecule, just where the oxygen is, you have the alpha carbon. So hopefully this video helps you a little bit with drawing the products of an aldol condensation. The one kind of tricky thing to watch out for is to make sure that the bulky groups are always E to each other, or trans if you prefer, going in the opposite direction so that they don't repel each other. So that's the Claisen condensation. General idea is redraw the original molecule, just where the oxygen is, make that the alpha carbon for the second molecule that you're drawing. That's how to think of this from the perspective of synthesis, but remember, you want to go back and make sure you understand what's happening in terms of the actual reaction, where you do the aldol addition and then do the elimination to get the degree of unsaturation there.